Hello, guys, welcome. And today we are going to be learning about another topic, which is the elements of queuing model. And I have documented a few things and did a bit of research, and I will read and explain a few things. So let's get underway. The elements of queuing model form the foundation of understanding how systems handle and manage waiting lines, a critical concept in optimization techniques. And queuing theory studies the behavior of queues in the waiting systems and helping optimize performance and minimize wait times and improve the utilization of resources. And these models are widely applied in industries like telecommunications, healthcare, streamline operations, and logistics. A queuing model typically consists of several core components such as arrival process, service mechanism, and the queue discipline, system capacity, and population source. So each of these elements play a very crucial role in the dynamics of defining the queue and also its efficiency. The arrival process describes how customers or entities enter the system. This is often characterized by the rate at which arrivals occur and whether their pattern is predictable, such as the Poisson distribution, which is commonly used in queuing theory. The arrival process also considers whether the entities um, come at random intervals or are scheduled. Additionally, it accounts for factors like batch arrivals, where multiple entities arrive simultaneously, and whether the arrival rate changes over time, influencing the system's ability to handle and demand fluctuations. Next, we will see about the service mechanism. It focuses on how services are provided to entities within the queue. It includes details about the number of servers available and the time taken for each server to react with the entity and the nature of the service. For instance, service times might follow an exponential distribution, which is a common assumption in basic models. The service mechanism also examines whether services work independently or in coordination, as well as whether they operate at fixed rates or at variable speeds. This element is crucial for determining the overall efficiency of the system and how quickly it can process the entities in the queue. Next, we will see about the queue discipline. It defines the rules for prioritizing entities within the queue. Common disciplines include first come first serve, which is FCFS, and where the entities are served is the last come first served, which is the LCFS, which prioritizes the most recent arrivals. Other methods such as priority based queuing assign higher importance to certain entities based on predefined criteria, and queuing discipline directly impacts the entities and the waiting time and fairness perceived by customers or entities, making it a vital factor in designing various efficient systems. Next, we will see another critical element, which is the system capacity, which refers to the maximum number of entities that can be accommodated in the queue or in the system at a given particular time. Systems can be finite, where a cap on the number of entities exists, or infinite, where no such limit applies. Limited capacity systems often result in entities being turned away or balking when the system is full. Understanding the constraints of the capacity helps in resource planning and ensures that the system remains functional under peak loads. Lastly, we will see the population source. It identifies the source of the origin of the entities and uh, the origin of the entities entering the queue. It could be finite, meaning there is a limited pool of entities, or infinite, where there is an unlimited pool of entities. Uh, this distinction affects how the arrival rate impacts the queue dynamics. For example, we will see in a finite source, systems are as more as the entities that enter the queue, and the arrival rate may decrease because few entities remain in the pool. Conversely, an infinite source assumes a constant arrival rate regardless of queue size. So, by understanding and analyzing these elements, optimization techniques can be applied for design systems that uh, reduce waiting times, balance workloads, and enhance customer satisfaction. Queuing models allow for better decision making and in the areas like workforce allocation, infrastructure, planning, and process improvement, making them an indispensable tool in modern operations. Thank you.